What's up guys, Major Math with another video on fluid mechanics. If you have any questions, drop it in the comments, and if you're having trouble with other problems, I've attached my email in the description, so please feel free to reach out. Without further ado, let's get started. Question 3.44 says if a 390 Newton force labeled as F1 is applied to the piston with a 4 centimeter diameter, what is the magnitude of the force F2 that can be resisted by the piston with the 10 centimeter diameter? Neglect the weights of the pistons, right? Alright, first things first, always think of what the goal is. Alright, so our goal is to find F2, right? So we're trying to find this force that can be resisted by the piston with a 10 centimeter diameter. Okay, so find F2 basically. We're given don't forget, it's kind of hard to miss this, but it gives us the liquid that's inside this has a specific gravity of 0.85. It says that force 1 is 390 newtons, so this force right here, it gives us, I'm going to label this as D1, okay, so diameter 1, I'm going to label this as diameter 2, okay, so diameter 1 is 4 centimeters, and diameter 2 is 10 centimeters. Alright, our assumptions, we're going to assume that there's no weight of the pistons, also they're frictionless. We're also, so we'll say frictionless pistons, and then the question already says weightless, so we're not going to write that. And we're also going to assume the oil is incompressible. Remember that incompressible just means that the density of the entire liquid is consistent throughout. We wouldn't be able to solve this problem if the density wasn't consistent throughout the entire liquid. I'll give us some, I don't even know how to do it, but okay, first things first, we're given specific gravity, so let's go ahead and convert this to find densities, right? So remember that, I'll show you the table that the textbook shows it on. Table F.2 says specific gravity right here. I don't want to write on this actually. It says specific gravity is equal to, let's actually do this to find specific weight. We'll need specific weight. So it equals specific weight of the liquid, in this case oil, over the specific weight of H2O at 4 degrees Celsius, which the specific weight for water at 4 degrees Celsius is 9,810 newtons per meter cubed. So write that formula down. I'm going to write oil right here, so that's what it is in this particular case, and then water at 4 degrees Celsius is this specific weight. We actually know SG, the specific gravity, I'm going to go ahead and write it, is 0.85, right? So I'm going to multiply, to find the specific weight of oil, I'm going to multiply 0.85 by 9,810 newtons per meter, meter cubed, and you will get the number of 8,338.5 newtons per meter cubed. So that's the specific weight of oil that's in that piston. Okay, so we gotta think about this. So we need some sort of way to determine, like, by using the force and the diameter, we need some sort of ratio or some sort of formula that relates this to this force and diameter over here. So quick little side note, this is going to be important. Let's do a side note here. So planar interface rule. Basically this rule states like, so you have like a vat of some unknown liquid, doesn't really matter. It's saying that the pressure here, pressure A, is going to be the same as pressure B over here because they're at the same horizontal level. But we know obviously that the pressure here and pressure here, they're on the same level vertically, but they will not, these pressures do not equal each other. The pressure is going to be a lot higher at the bottom of this pool or vat or whatever it is at pressure point B than it is at point A, right? So using this rule, we can actually absolutely help us, right? So let's looking at this right here, say that this point right under here at this, right under the piston, this is point A, right? And then at the same horizontal level, point B. We know, say this top part of the whatever this is, I don't know, I'm just going to call it a container. To say this top part of the container is not here, right? And these were at the same level, there's a piston right above. These pressures would be equal to each other because they're at the same horizontal level, and we know that by using the planar interface rule. But that's not the case. We actually have all this depth, so we know that's not equal because it's so much deeper. There's all this oil, all of it is because of gravity is pushing more and more force down on top of this. So the way we can do this, so say, right, so we know pressure A equals pressure B if there wasn't that top half, okay? But we know there's that top half, so how do we fix this? So we know, we'll say this, I'll just write it down. We know that we can balance this out. They will be equal to each other if you take into account for this top part using the formula specific weight times height. Okay, so you might also be thinking, how did I get this right here? Okay, so I should talk about this in my lesson, but this would be good for the video too. Let's think about pressure, right? That's what we're looking at. We're looking at pressure. Pressure is force over a given area, right? And that's what the units tell us, and that's what the definition is. In this case, the force is weight, right? Because it's just that water, that oil just keeps, the weight keeps adding up over and over until we get to that, close to that bottom. And it's just, that's why the deeper you get down, the more higher pressure there is. So we know that in this case, and in a lot of cases as well in fluids, it's just the weight, force of weight. We know that the definition of force of weight is mass times gravity, right? So mass over gravity over a given area. Okay, and then we can rewrite this mass. We know that density equals mass over volume, right? We can rearrange this, say mass equals density times volume, okay? So we rewrite that mass. We can also rewrite this area. So in this case, we have a circular area, right? Because it's giving us the diameter. The picture doesn't seem like it's a circle or tubes or whatever it is, but it is. Since it's giving us diameter, we know that these pistons are circular. So we know the area of a circle is pi r squared, or you can also write it as pi over 4 times diameter squared. Okay, so let's rearrange that, rewriting it with these, right? Density times volume times gravity. I'm getting ahead of myself, one sec. And then let's rearrange this. We know that the specific weight is density times gravity, so let's rearrange that. So then we end up with this, okay? Actually, I got ahead of myself as well. We'll get back to this later. We will have to use this later. But let's keep this as A for now. Keep this in mind because we will use that later, that area. And then if we think about volume, length times width, or whatever it is. In this case, it's a circle. So we could actually, this is actually helpful to, let's write this out, right? Oh, no, that's fine. Okay, so we know that, and then we know that volume, we can also write that as area times height, right? Okay, so we can also write like that. Let's go ahead and write that. And then we can cancel these out, and we're left that pressure equals this, right? So that's how we got to this. You don't have to do this. I was just showing it out. You don't have to do this every time. We know just in a simple closed system like this, or the example problem, that the pressure is going to equal the specific weight times height. So I was just showing how I got there, but we can just keep that in mind for further videos. So that's how I got this, right? Back to what we were doing, we know that pressure A here will equal pressure B plus specific weight times height, right? Using that planar interface rule, and then using that pressure equation I just derived. Okay, so this is going to be helpful. We say that F1 over F2. So the force of the weight of the piston 1 over the force of the weight of piston 2 will equal the so I kind of skipped a step here. I'll explain it in a second. I didn't mean to write it. You know what? That's confusing and stuff. So let's write that equation we have. Pressure A equals pressure B plus specific height, right? And like I just said earlier, pressure is force over area. So let's rearrange that. Say, in this case, the force is weight, right? So of point A, point B equals God damn it. Let's put area. So point A and point 1, they're at like the same spot. Okay, and then we can't forget this, right? So all I did was rewrite the same equation we already figured out using planar interface rule and that pressure we derived. Okay, so we need to solve for the diameter, or the force 2, right? So force 2, it's actually this. So I'm gonna rearrange these. I don't like that I'm using A and B. Or do this as 0.1, 0.2. So we need to find this force 2, which I just realized is not force of weight. Okay, it's the actual force. Okay, so we need to find F2, right? So let's rearrange this to get F2 by itself. I'm just putting this O for oil. Putting that O for oil is what I said earlier. Okay, so I just did some algebra, rearranged it. Now we need to know, how do we find area, right? So like I said earlier, area is pi over 4 times diameter squared for these circular pistons. So we can go ahead and plug those in. I think I forgot to mention too, we are given this height. You can see from this diagram here. So we are given the height. So that is another given I should have wrote earlier. Okay, and then we can actually cancel these out, right? So this is actually set up perfectly for us to solve, and we can find the force force on piston 2. Let's go ahead and plug everything we know in. So we know that the force acting on piston 1 is 390 newtons. Sorry, I can't see. And then we know that the diameter of piston 2 is 10 centimeters. We should convert that to meters. So divide it by 100. Okay, and then just do a conversion there. Don't forget to square it. And then we need to do the same for diameter 1, which is 4 centimeters. And I'm not going to write the conversion here. I'm just going to write it as 0.04 meters. We'll square that. And then minus the specific weight, which we found. 8.5 newtons per meter cubed, times the height, which is 2 meters, times the area, right? Yeah, pi over 4, diameter, so that's the same as 10 centimeters. I just divided by 100, and then I squared it. Okay, if you put this all in the calculator, you will get that force on piston 2 is 2,306.5 newtons. If you want to convert that to kilonewtons, it will be about 2.31 kilonewtons. And that will be the force acting on piston 2, and that will be our answer. Okay, so we know this formula. Force equals surface tension times length of the wetted perimeter, okay? And we also know that force of the weight is equal to mass times gravity, okay? So, and then we have this right here. We know that from what we know in statics, and this is in equilibrium, right? This is what it's going to look like with that, like at any moment in time when you have these two walls. So we know that the force of surface tension is going to equal the force in weight, right? So we gotta, I'll do this too. We know we can plug this in right here, and we can plug mg in right here, right? And before we do that, let's rearrange, because we gotta find, like, we don't know where we're gonna, how do we find height from this? How do we implement the variable height into these equations that we know we gotta use? So we gotta do some rearranging. So let's rearrange this weight one first, right? So let's look at mass. How do we rearrange this mass to get height involved, or this force of weight? So we know that density equals mass over volume. We can rearrange that to density times volume equals mass, right? So let's go, and then we'll just go ahead and rearrange the volume, right? So we know from the volume we can get the variable height from it. So let's rearrange it again and say that volume is equal to length times width and height, right? Because we're dealing with a rectangle here. So length times width times the change in height, right? So now you can see where we're getting this variable height from, and we can actually end up solving this. And this equals mass, okay? So let's plug this in for mass. So rearrange this to density times length times width times height times gravity. Okay, and then we need to rework this to make this represent the wetted perimeter. So when we're looking at this, what is going to be the wetted perimeter? So it's just two walls. There's nothing like in front. We're not taking a cross section and looking at this. It's really just those two walls. So the perimeter is just going to be the length of the whatever, how deep this goes back. See what I'm saying? That's going to be the length. So this is just going to be, is just going to equal, the water perimeter is just going to be 2 of the lengths, right? Because it's just 2 walls. So let's go ahead, and this is the main equation we're looking at. Let's plug this in for there, and let's plug in this right there. Let's go ahead and do that. Density times length times width times height times gravity. We see that we have a length on both sides, so we can actually go ahead and cancel it out. So we end up not needing to know the length, which is useful. We know the width, right? It's separated by 1 millimeter apart. So we know that this is that 1 millimeter or 0.001 meters. And then we know density from the textbook. It's up here, written right there. Oh, no we don't. Do we need density? We might need density. No, we don't need density. We could use density of this, but we can also do, we know that specific weight is density times gravity, so we can actually just rearrange this to look like, right, because specific weight equals density times gravity, so we can just replace this density and gravity with just specific weight. That's what I did in my notes, sorry about that. And then and we need to solve for the change in height. So let's rearrange this to solve for change in height. Right. I did that backwards, didn't I? Right. So I just divided by specific gravity and the width, moved it over. Okay, so we're left with this formula, and we can go ahead and plug everything we know. So this will equal 2 newtons per meter over specific weight, 900. Width is 0.001 meters. Change in height, if you put that in the calculator, we'll get 0.015 meters. Multiplied by 1,000, it's 15 millimeters. So the max capillary rise will be 15 milliliters. Thanks for watching, soldiers. Don't forget to leave a like and subscribe for more content like this. If you have any questions, leave it on the comments, and if you need help with any other problems, feel free to contact me with the email shown on the screen.